Okay. Now, talking about partial derivatives a little bit. First of all, let's consider just a plain old derivative. A derivative with respect to x of sine of x squared is how fast the sine of x squared is changing with respect to x. And the question is, if you got a little change in x, what kind of change does that make in the sine of x squared? Well, a little bit of change in x causes a change in x squared. And of course, the rate at which x squared changes with respect to x is the derivative of x squared, 2x. So 2x is how fast x squared changes due to changes in x. Once you have a change in x squared, that causes a change in the sine function. And the rate at which the sine function changes due to little changes is derivative of the cosine. The derivative of the sine is the cosine. Okay, so this is how fast the sine of x squared changes due to a change in x squared, not a change in x. If you multiply how fast x squared changes due to a change in x by how fast the sine changes, sine of x squared changes due to a change in x squared, you get how fast the sine of x squared changes due to a change in x. So the sine changes because x squared changes, and this is the rate at which that happens, and x squared itself changes at a rate of 2x. Okay, that's how fast x squared changes. You multiply how fast this changes. You think of a change in x squared as driving the change in the sine function. So x squared changes by this much, then that change goes into this function. A little hard to say that, so I'm going to back off and not say it. Think it through. Okay. Don't have a good set of words to put around that, or at least nothing better than what I've done here. It was earlier in the day, maybe. Okay. So, let's look at another example. We want the derivative with respect to t of sine x, where x depends on t. The dependence is x equals t squared. So again, t changes by a little bit. T squared changes. That change goes into the sine of x, so x changes by whatever t squared changes by due to the little change in t. So what we do is we multiply. Now, okay, I'm going to let f sine of x, I'm going to let f of x stand for the sine of x, so I can write out the formula for this chain rule, okay? So again, if f of x is the sine of x and x is t squared, then when we multiply the rate at which t changes due to a small change in t by the rate at which the sine of x changes due to that change in x, resulting change in x, we get the rate at which this sine function, the function f of x, changes due to a change in t. And we're multiplying, again, this is the rate at which the sine function changes due to a change in x, and this is the rate at which x changes in response to a small change in t. In this case, now, df dx would be cosine of x, and dx dt would be this. Okay, and of course, now since x equals t squared, right there is our result. And this result is consistent with what we did up here. Okay, so this is essentially the derivative of the sine of t squared, since x equals t squared. Okay, so we could also, of course, just directly do the derivative with respect to t of the sine of t squared, and we would get the same thing. So you should probably write that out, work that out. You're asked to do that sort of thing in the homework. And let's go to a little more extensive example. The idea is simple if you keep in mind that we have to multiply how fast this variable changes due to a change in x, or this one changes due to a change in t, by how fast this changes due to a change in whatever this thing is. Okay, so let's look at it down here. Okay, we want the derivative with respect to t of the sine of x squared y cubed, where x equals cosine of t and y equals tangent of t. Now that's kind of a weird function. I can't imagine how that could arise, but we can do it. Okay, well, this is a function of x and y. So sine of x squared y cubed is a function of x and y. X will be the cosine of t, y will be the tangent of t. This function here, the sine of x squared y squared, is driven, okay, if t changes by a little bit, then that causes cosine of t to change a little bit, which of course causes x to change by a little bit. So we multiply the rate at which a small change in t changes the value of x, and then we multiply that by the rate at which a change in x drives a change in the sine. Okay, so at what rate does x change with respect to t? Well, that's dx dt. And at what rate does the sine change due to a change in x? Well, that's your derivative of this function with respect to x, partial derivative in this case. Okay. Well, that's not, the change in x is not the only thing that's caused if t changes. T also causes y to change, and that causes this thing to change. So we have to take the rate at which this changes, which is your dy dt, and multiply it by the rate at which the sine changes due to a change in y. There it is. Partial def with respect to y times derivative of y with respect to t. Now we can calculate that. Partial of this function with respect to x is 2x cosine of x squared y cubed. And derivative of x with respect to t, well, that's derivative of the cosine. That's times the negative sine of t. Then we have the partial, okay, we have the rate at which a change in y changes, a change in t causes, the rate at which a change in t drives a change in y, multiplied by the rate at which a change in y drives a change in the value of the sine function. And that's going to be then plus what? The derivative of this function with respect to y is, incidentally, I didn't do my derivatives, right? I left off the y cubed. Okay, the derivative of the inner function there with respect to x is 2x y cubed. The derivative of x squared y cubed, the derivative of the argument of the sine function with respect to y, is 3y squared times x squared times the cosine of x squared y cubed, multiplied by the derivative of the tangent with respect to t, the rate at which t changes the value of the tangent, therefore the value of y. That's your dy dt, and that's 1 over 1 plus t squared. Now we can do this whole thing in terms of t. So x is a cosine of t, so we get 2 cosine of t y is the tangent of t, so there's going to be a tangent cubed of t, times the sine of t. Of course, that's a negative sine of t. There's a negative sign out in front here. Yeah. And then this term, which is going to be 3, y squared is going to be tangent squared t. X squared is going to be cosine squared of t. And then you have the cosine of x squared y cubed. And I didn't write the cosine of x squared y cubed here. Okay? And that was an oversight, but I get away with it, because I'll just factor it out, since this is a factor of both terms. We're going to have the cosine of x squared, which is a cosine squared of t, y cubed, which is a tangent cubed of t. Probably want to do a little more group in there to make sure it's clear. Now, it's about as clear as mud, probably, but we notice, of course, that the tangent of t has a cosine in the denominator, sine over cosine, so it's going to simplify. This is going to simplify, and this is going to simplify a bit. I'm not going to go to that extent. Just want to illustrate how the chain rule works. Again, what we're doing is saying, if t changes by little, then x changes by little, and y changes by little. The rate at which x changes is the negative of the sine of t. So there's the rate at which x changes, negative sine of t. And then if x changes, sine of x squared y cubed changes at the rate 2xy cubed cosine of x squared y cubed. That's your change in f with respect to x. But f also changes due to the change in y. And there's the corresponding term, and then we can write all of this in terms of the parameter t if we wish. Of course, we could have written this function totally in terms of t. This would be the sine of the cosine squared of t times the tangent cubed of t. And then we could just do our regular rules for derivatives. And it's worth working that out, but of course Open Math, WebAssign is going to have you do that sort of thing. All right. Now, you think that's starting to get a little complicated? It gets even better. Then, of course, it generalizes. You could have a sine of 5 or 6 variables here, each one parameterized in terms of t. It'd just be longer. It wouldn't be any harder. You just keep your wits about you and write out all the terms. It takes a little practice. You've got to look at a few examples, but it's not particularly difficult to do. Once you've practiced it a bit, and especially once you understand hopefully what I'm telling you, instead of just understanding a bunch of rules. It's fine to just understand the rules, but you understand the rules better if you understand how a change in t makes both x and y change, and you got to do that, and so forth. Okay, over here, you're going to love this one. Okay, say you want the derivative of x squared plus y cubed, where x depends on both u and v, and so does y. Well, then a change in u is going to cause a change in x, right? And a change in v is going to cause a change in x. So you're going to need the rate at which a change in u drives a change in x, that's this, times the rate at which a change in x changes the value of this expression. Then you need the rate at which a change in v causes x to change, multiplied by the rate at which the function changes again with respect to x. And then we've got the same thing for y, because a change in u will drive a change in y, which will then drive a change in this expression. And implicitly, x squared plus y cubed is your F function, I guess maybe I can write that out. And it's not derivative with respect to t. Okay, I'm really not thinking completely clearly, because what I'm writing out is a differential. So I'm going to change what I've written here a little bit. First place, this is a partial derivative with respect to, we'll do a partial derivative with respect to u. And what I've written out here is valuable. That's, you could call your total differential or your total derivative, whatever. So I'm gonna stop this video and just do another one on this situation.